In this video, we're going to work example problems from the opening section of Chapter 2, which was on the parallel postulate and special angles. Now, these special angles that they're referring to are when you've got a transversal cutting across two lines, and specifically when those two lines are parallel, there's some special relationships between the angles that result. Any transversal that cuts across two lines, whether they're parallel or not, those two lines are parallel or not, there's going to be four angles created. And we talked about the naming convention for those angles. You've got corresponding angles, so like 1 corresponds to 5, 2 corresponds to 6, etc. You've got, let's see, there's the interior angles, 3, 4, 5, and 6, the exterior angles, 1, 2, 7, and 8. You have alternate interior angles. So of the interior angles, you alternate the vertex and you go across the transversal. So 3 and 6 are alternating interior angles, 4 and 5 alternating exterior, or 1 and 8, 2 and 7. So you've got these different angles. All of the names that I just talked about apply to any transversal cutting across two lines, whether or not those two lines are parallel or not. However, when those two lines happen to be parallel, then we learned there's some theorems that we could develop that related the angles. If the two lines weren't parallel, then the only thing we could say based on our previous knowledge is that we have the vertical angles are congruent, and we could see that like 1 and 3 are supplementary, 2 and 4 are supplementary, 1 and 2 are supplementary, etc. 1 plus 2 plus 3 plus 4 is 360. But other than that, there was no special relations between the angles. But we learned that when the two lines are parallel, there's additional special relationships in the sense that corresponding angles are congruent. So again, you come to this vertex, the top left corresponds to, on this vertex, the top left. So 1 and 5 are congruent, 2 and 6 are congruent, 3 and 7, 4 and 8. Also, alternate interior angles are congruent and alternate exterior angles are congruent. That wouldn't be the case if the lines weren't parallel. So, okay. The measure of angle 1 is 108 degrees. Find the measure of angle 5 and the measure of angle 7. So the measure of angle 1 is 108 degrees. So what does that mean that the measure of angle 5 is? Well, those are corresponding angles. So this is also going to be 108 degrees. What about angle 7? Well, we can use the fact that angle 5 and angle 7 we see are supplementary. So what is 180 minus 108? That's going to be 72 degrees. Okay, if the measure of angle 3 is 71 degrees, find the measure of angle 5 and the measure of angle 6. So, okay, bottom left. So these aren't corresponding. Okay, so what we also learned that interior angles on the same side of the transversal are supplementary, and same with exterior angles. So we know that angle 3 and angle 5 are supplementary. So we can, the measure of angle 5 is going to be 180 minus 71, and that should be 109, I think. Yeah. Okay, what about the measure of angle 6? Well, alternate interior angles. Measure of angle 3, measure of angle 6 are the same. So 71 degrees. Okay, the measure of angle 2 is 68.3 degrees. Find the measure of angle 3 and measure of angle 6. So vertical angles, 2 and 3. So this is going to be 68.3 degrees. And the measure of angle 6, alternate interior angles, 68.3 degrees. And again, I just want to point out that this only works because L and M are parallel. They've stated that. Okay, if measure of angle 4 is 110.8 degrees, find the measure of angle 5 and the measure of angle 8. Those are all going to be congruent, alternate interior and then vertical. So all right, does the relation is parallel to have a reflexive property, a symmetric property, and a transitive property? So we're not getting too much into math proofs. and like properties and stuff. But I thought I would include this question because it's pretty interesting to think about. So remember, the reflexive property is that it's like, okay, what about, does the relation greater than, let's answer that question, greater than. So you have like one number is greater than another number. Is that reflexive? Is that symmetric? Is that transitive? Well, the idea of reflexive is, so you take the same number and you put in that operation. So A is greater than A. That's not true, right? So it's not reflexive. Is it symmetric? So in that case, you use two numbers. You say A is greater than B. Okay. Now, can you flip the numbers and do B is greater than A? No. So it's not symmetric either. Now, is it transitive? That what you do is you say if A is greater than B and B is greater than C, then must A be greater than C? Yes. So it is transitive. That's the idea. Like the equal sign. A is equal to A. Yes, that's reflexive. Okay, if A is equal to B, then is B equal to A? Yes, that's symmetric. Okay, if A is equal to B and B is equal to C, then is A equal to C? Yes, it's transitive. So since it satisfies all three, it's called an equivalence property. That's the idea of these properties. So now what they're asking is, we want to do the same thing with parallel to. So can you have A be parallel to A? Can a line be parallel to itself? No. That doesn't satisfy both of the parameters of the definition of parallel. They have to not intersect. Well, if it's the same line, they obviously intersect. They're on top of one another. But then if they're the same line, they can't be contained within a unique plane either, because that's a part of parallel, right? You have to not intersect and be contained within one unique plane. Well, one line or two lines on top of one another, there's an infinite number of planes that go through those lines. So no. Okay. Now, if A is parallel to B, it's not reflexive. No. If A is parallel to B, okay, can we flip that and can we say that B is parallel to A? Yes. So it is symmetric. What about transitive? Okay, if A is parallel to B and if B is parallel to C, then is A parallel to C? That's really interesting. Let's think about this. That's why I wanted to include this question. I think it's intuitive to think about these ideas. So my gut tells me that the answer to this is no. Not necessarily. It could be, but it's not like universally true. So if you have, here's line A, and here's line B. Okay, so line A and line B. Okay, they're parallel, contained in this same plane here, plane P. Okay, now, yes, if you put C in the same plane P here, then it is true that B is parallel to C and then A is parallel to C. But again, this has to be universally true for all scenarios. So what we can do is, we're not going to draw a line that's like a skew line, because we need to make B parallel to C. So what we can do this, kind of in the back here, we'll make another line back behind this plane P. This is line C, and B is parallel to C. By the definition of parallel, we've got this other plane here. Plane Q. All right, now does that mean that in this case that A must be parallel to C? Okay, actually the answer I think is going to be yes. I was thinking it would be no, but I was thinking it was going to be no because they can't all be parallel to each other, but that's not what it's asking. We're just saying if A is parallel to B, okay, and B is parallel to C, then does that automatically mean that you can state A is parallel to C? Yes. You can't state that they're all parallel to each other, but you can state it like the reason why this is a yes is because if you're, all you need to say is that when you say A is parallel to B, in order for a new line to be able to be parallel to not A and B at the same time, but parallel to both A and B separately, which is what we're doing here, you just need, that line needs to not be skew with either A or B. And that's the main idea. Once we said that B was parallel to C, that this automatically says that, okay, 100% C is not skew with B, of course. But then because A is parallel to B, C can't be skew with A either. It can't be. So that means that automatically A is going to be parallel to C. Okay, so yeah, that's the idea. The answer is yes. All right, in a plane, L is perpendicular to M and T is perpendicular to M. By appearance, how are L and T related? So, okay, let's just use the plane of our computer screen. I'm going to continue to point this out throughout this entire course, but let's say we take some random plane in 3D space. And now we're going to rotate 3D space to where we're looking straight at the plane. That's the computer screen here. Okay, so it's saying that L is perpendicular to M, and I want to draw this in just some, remember, perpendicular doesn't mean you have to be going left to right and up and down. Okay, so let's see. L is perpendicular to M, and we could go ahead and you could still, even though the definition of perpendicular doesn't imply 90-degree or right angle, it's still convention to do that because we proved the theorem that if they are perpendicular, there is a right angle created between them. Since that's true, those are interrelated. We know that now. We can go ahead and put the box. It's just if you're trying to prove a theorem, if you're dealing with the idea of something being perpendicular in the context of proving a theorem or a proof, then you wouldn't put that because you're trying to be rigorous. But just in general practice, you could put that box if you see perpendicular. Okay. So L is perpendicular to M, and T is perpendicular to M. So we'll do this. Okay. Now you might say, oh, well, look, they're perpendicular. Well, no, they didn't say that. In fact, what they're asking is, by appearance, how are L and T related? They seem to be perpendicular. So that could be another theorem that we were probably going to get into in the upcoming sections. That if you have one line is perpendicular, oh no, it did say they're perpendicular. I'm sorry, they are perpendicular, but by appearance, that seems to mean that L and T are parallel, and that's what they didn't tell us. It seems that L is parallel to T. So a theorem that I would guess is coming up in the upcoming sections is that if you have two separate lines are perpendicular to the same line, then those two lines must be parallel. It sure looks like it, and to me that would make sense, and that's what you would do the proof for. All right, suppose that R is parallel to S. Okay, R is parallel to S, and then we've got this transversal we can see here. Both interior angles 4 and angle 6 have been bisected. Angle 4 and angle 6 have been bisected. Using intuition, what appears to be true of angle 9 formed by the bisectors? Okay, so we've got these two parallel lines cut by a transversal. So now all of those theorems about these special angles apply. Okay, now both interior angles, what does that mean? Both interior angles. There's 4 interior angles, so I don't know what they mean by that. There's 4 interior angles, so 2 of them have been bisected, angles 4 and angle 6. Okay, so by intuition, what appears to be true of angle 9 formed? Well, they're probably going for it. It looks like it's going to be perpendicular, but visually it looks like that. But why would that be true? Well, okay. We know that angles 4 and angle 6 are supplementary. They're the same, they're interior angles on the same side. So that would mean that, I guess, these two would be complementary, maybe. Okay, if angle 4 is, the measure of angle 4 is x, and the measure of angle 6 is y, then we know that x plus y is equal to 180. But if they've been bisected, then you can say it's like you could divide x by 2 and y by 2, and which means, so yeah, those are complementary, these two. So let's call this theta and this angle alpha of this triangle. So theta plus alpha is equal to 90. Well, the sum of the angles of a triangle are 180. So that means angle 9, the measure of angle 9 must be equal to 90. So it's a right triangle. That was more of an unofficial engineering proof there. Okay, suppose that R is parallel to S and the measure of angle 2 is 87 degrees. All right, two parallel lines cut by a transversal. Well, the measure of angle 3 is going to be 87. Those are vertical angles. The measure of angle 6, opposite interior angles, is going to be 87. The measure of angle 1 is going to be, so 1 and 2 are 1 and 2 are, yeah, 1 and 2 are supplementary. You might say, well, why didn't we say 1 and 3 are supplementary? Remember a tip that they gave us in the book that when you're doing calculations, try not to use, if you can, what you've already calculated. Use what was given. Now, in this case, it doesn't matter, but it's good practice to use, instead of saying, okay, we can find angle 1 by saying 1 and 3 are supplementary. Well, because we calculated as part of the problem measure of angle 3, but we were given the measure of angle 2, so use that as much as you can. Use what's given already for calculations as much as you can. Avoid using what you've already calculated, because you can have like numerical roundups, rounding errors can come into play. Not in this case, but in other cases. So, all right. Since measure of angle 1 plus measure of angle 2 is 180, then the measure of angle 1 is 180 minus 87. 7, 3, 9. So, okay, 93 degrees. Okay, now measure of angle 7, we've got, let's see. Those are not corresponding. Those are exterior angles on the same side, so those are supplementary. Angle 1 and angle 7 are supplementary. So 180 minus 97 is going to be 87, yes, because, well, 7 and 6 are vertical angles. So there we go. In Euclidean geometry, how many lines can be drawn through a point P not on a line L that are parallel to line L or perpendicular to line L? All right, so remember, this idea of Euclidean geometry was that, so if you have the perspective is if you have a plane, then it's like perfectly flat, and the idea is if you've got any 2 points, different points within the plane, and you draw a line between them, both those points are in the plane, you draw a line between them, then the entire line is going to be contained within the plane. That's the perspective of Euclidean geometry that we were told to view Euclidean geometry from. So, okay, with that, then if we've got some plane here, plane C, so now there's a point P not on a line L. Okay, they don't give us any information about a plane, so, but that should come into play here still. So we've got some point P. Let's just say it's in the plane. Could be in any plane, right? You could draw an infinite number of planes through a point, but let's just think about this plane. And then there's going to be this line L that we can also say is in the plane. Because if you think about it, if you've got a line and a point that's not on the line, then that's going to constrain a unique plane, right? A line and a point not on the line are going to constrain a unique plane. So we have a point P and a line that's not on, doesn't go through point P. They gave us that. And now that defines a unique plane, and I'm just saying that's plane C. So it's completely general, right? So how many lines can be drawn through point P that are parallel to line L? Well, it's going to be one and only one. That was a theorem. Oh, no, that was the parallel postulate, the part of the title of this section. That was the parallel postulate, okay? Now, what about perpendicular to line L? Same idea, just one. There's only one line that goes through point P and it's also perpendicular to line L. Only one. All right, lines R and S are cut by transversal T. Which angle corresponds to angle 1? So remember, corresponding, this has nothing to do with, well, yeah, they didn't even tell us this. So it says lines R and S are cut by transversal T. It doesn't even necessarily mean that R and S are parallel. It doesn't tell us that. So maybe they aren't parallel. We don't know. But this notation applies to any case where you have a transversal cutting across two lines, whether or not those lines are parallel or not. So what does corresponding angles mean in this situation? Well, you come to one vertex and you think about, okay, there's top left, top right, bottom left, bottom right. Then you go to the other vertex and those same positions, with like the top left, that corresponds to top left over here. So 5 and 1 are corresponding. You see, 2 and 6 are corresponding. 4 to 8 are corresponding. Okay, which angle is the alternate interior angle for angle 4? Alternate interior, that's angle 5. What about alternate exterior? Yeah, so all of these are the interior angles, 3, 4, 5, and 6. And 1, 2, 7, 8 are the exterior angles. So alternate interior, you're focusing on all of the interior. If they're alternating interior, they're across from each other on across from the transversal. And same with the exterior. Alternate exterior to angle 1 is angle 8. Is the other interior angle on the same side of the transversal T? Which angle is the other interior angle on the same side of the transversal as angle 3? The other interior angle on the same side of the transversal, that's angle 5. Okay, AD is parallel to BC. AB is parallel to DC. Okay, AB is parallel to DC. AD is parallel to BC. And the measure of angle A is 92 degrees. So find the measure of angle B, measure of angle C, measure of angle D. So, yeah, what they want us to do is think about this idea of parallel lines and transversals. So, okay, what we want to do is extend these out like that. Okay, so we've got like AD and BC are cut by transversal AB and DC. And then AD and BC are parallel lines cut by transversal, or no, AB and DC are parallel lines cut by transversals AD and BC. You see, there's separate cases here. So, all right, measure of angle A is 92. Okay, so if we look at, so AB and DC are parallel, right? And we can think about those are cut by the transversal AD. So what can we do with this? We can think about opposite interior angles. That means this is going to be 92 degrees. This angle here, so let me make it clear. Okay, that's 92 degrees, right? Now, what else can we do? Well, this is 92 degrees, vertical angles. This is 92 degrees. Now, we've got supplementary angles here and here, so 180 minus 90 is 90, but this is going to be 2, since 92, this is going to be 88. So that means vertical angles, this is going to be 88. Opposite interior angles, 88. Okay, so now we can look at the perspective of AD and BC are parallel and cut by the transversal AB and BC. So here's opposite interior angles in that sense. And then we've got vertical angles here. Opposite interior angles again. Vertical angles here. 88, opposite interior angle here. And then opposite interior angles. There we go. So now, but let's just match these up. What is measure of angle B? That's 88. What is the measure of angle C? That's 92. What is the measure of angle D? That's 88. All right, L is parallel to M with transversal T. Okay, and ray OQ bisects angle MON. If measure of angle 1 is 112 degrees, find the following. Okay, measure of angle 2, measure of angle 4, measure of angle 5. Well, we can see the measure of angle 4 is going to be equal to the measure of angle 1. That's vertical angles. We could just, that's an easy answer there. Okay, now, so L is parallel to M, and we're cut by this transversal. So we've got this parallel lines cut by a transversal we can work with to get angles. So, all right, well, we know 4 and 5 are going to be congruent. Do they act for 5? Yes, because that's opposite interior angles. So, all right. What else? We know that 1 and 2 are complementary or supplementary. So 180 minus 112 is 68. Okay. Now what else? Okay, OQ bisects MON. So, okay, now these are opposite interior angles, right? So what that means is that the measure of angle MOQ is going to be the measure of 1/2 times the measure of angle 3. Because we know that this entire angle here is congruent to angle 3, opposite interior angles. But we also know that OQ bisects this entire angle, so that means that this angle MOQ is half of the measure of angle 3. Okay, do we have angle 3? No, but we should be able to get it. No problem. Yeah, it's vertical to 2, 68 degrees. So what is 68 divided by 2? 34 degrees. Okay, same setup, but now we've got measure of angle 1 is 4x plus 2. Measure of angle 6 is 4x minus 2. Find x and the measure of angle 5. So, okay, how are 1 and 6 related? Are those corresponding? No, 1 corresponds to 5. Those are exterior angles on the same side of the transversal, which we had a theorem that said those are supplementary. So that means that the measure of angle 1 plus the measure of angle 6 is equal to 180. So 4x plus 2 plus 4x minus 2 is equal to 180. That's 8x is equal to 180. So x is equal to 180 divided by 8. 8 times 2 is 16. Okay, once again, 16. 8 times 5 is 40. So 22.5 is x. Now, what is the measure of angle 5? Well, okay, corresponding angles are congruent. 1 corresponds to 5. So the measure of angle 5 is equal to the measure of angle 1. So what is the measure of angle 1? Let's plug in x for the measure of angle 1. So 4 times 22.5. Let me... plus 2, so 92. So... there we go. All right, so M and N are parallel, cut by transversal K. They give us expressions for the measure of angle 3 and measure of angle 6. And so 3 and 6, we can see are opposite interior angles. So let's set the measure of angle 3 equal to the measure of angle 6. Okay, now let's just solve for x. Looks like we're going to get a quadratic equation here. So x squared minus 5x plus 4x, that's minus x, and then minus 20. But the x squared subtract out, so it's not going to be a quadratic equation. Adding 3x to both sides, so minus x plus 3x is 2x. Okay, adding 20 to both sides. So x is equal to 10. Okay, now the measure of angle 4, that's x. Now the measure of angle 4 how is that related to either one of these? So it's supplementary with angle 3. So we can, what is the measure of angle 3? X squared minus 3 times x. Okay, but the measure of angle 3 is supplementary with the measure of angle 4. So if we take 180 minus 70, we get 110. So the measure of angle 4 is equal to 110 degrees. Okay, same setup here, but now they give us measure of angle 1, measure of angle 2, measure of angle 8 in terms of x and y, and we want to find x, y, and the measure of angle 8. So, okay, how is the measure of angle 1 and the measure of angle 2 related? Well, okay, we could see actually, let's start off with measure of angle 1 and measure of angle 8. That's opposite exterior angles, so those are equal. So let's set the measure of angle 1 and the measure of angle 8 equal to each other. So subtract 3x from both sides, subtract 5y from both sides. Okay. Let's see. Now the measure of angle 1 and the measure of angle 2 are supplementary. So 5x plus y plus 3x plus y is equal to 180. So we've got 8x plus 2y is equal to 180. Okay, so now let's solve this system of equations here. So we've got, let's see, we can multiply the top equation by 4. So we get 8x minus 16y is equal to 0, and then 8x plus 2y is equal to 180. So minus 16y minus 2y is minus 18y, and then 0 minus 180 is minus 180. So 18 times 10 is 180, so y is positive 10. Now we can substitute for y into the first equation here. So 2x is equal to 40, x is equal to 20. So there we go. There's x and y. Now what is the measure of angle 8? So, okay, just plug it in here. So 3 times 20 is 60. 5 times 10 is 50. So 110. Okay, same type of problem, just some different angles. So, okay, angles 3 and angles 5 are going to be supplementary. This M and N are parallel. We have to make sure that's true, right? You have to verify this before you can make these relations. So they are parallel. So we've got, okay, 3 and 5 are supplementary. 6x plus y plus 8x plus 2y is equal to 180. So 14x plus 3y is equal to 180. Okay, what else? 3 and 6 are alternate interior angles. So 6x plus y is equal to 4x plus 7y. Subtract 4x from both sides. Subtract 7y from both sides. Divide both sides by 2. Okay, so x minus 3y is equal to 0. Now we can go ahead and just add these two equations. So 15x is equal to 180. So what is 180 divided by 15? It's 12. So x is equal to 12. What does that mean? Y is equal to, so 12 minus 3y is equal to 0. 3y is equal to 12. Y is equal to 4. Okay, now the measure of angle 7, let's see. 2 and 7 are congruent, right? Alternate exterior angles, but 2 and 3 are congruent. So the measure of angle 7 is going to be equal to the measure of angle 3. So measure of angle 3, 6 times 12 plus 4. That's 72 plus 4, 76. So the measure of angle 7 is 76 degrees. Okay, in the three-dimensional figure, segment CA is perpendicular to segment AB, okay? Segment BE is perpendicular to segment AB, okay? Are lines CA and BE parallel to each other? No, this is a case of skewness, right? It's like asking in the 3D coordinate system the x, y, and z axes, right? Well, the x-axis is perpendicular to the y-axis. The z-axis is perpendicular to the x-axis. The y-axis is perpendicular to the z-axis, but, well, I guess this is kind of hard to see because they intersect, but let's say they hypothetically didn't intersect. Let's say you had like the x-axis over here and the z-axis over here. It's skewness. There is a case where you can say that, like, if they would have said that, I think what they're going for here is if you say that CA is perpendicular to AB, and at the same time, AB is also perpendicular to FB, well, then FB is parallel to CA, but you need more constraints, right? Like you can, it's like there is a case where if you have one line is perpendicular to another line, and then another line is perpendicular to that same line, then there is a case where that means you can prove that two lines are parallel, but you need more information, right? FB, we could maybe say, look, since CA is perpendicular to AB and FB is also perpendicular to AB, then FB and CA are parallel. There are circumstances where you can say that, but you have to have more information, though, because BE is certainly not parallel to CA. They're skew. All right, in triangle ABC, line T is drawn through vertex A in such a way that T is parallel to BC. Okay, so you get this triangle ABC, T is drawn so where it goes through vertex A, point A, and then it's parallel to BC. Okay, which pair of angles are congruent? So yeah, what they're going for here is that, you know, even with a triangle, it's still we can still analyze a problem, break it down to see, okay, look, we've still got these two lines T and line BC are parallel, two parallel lines, and they're cut by transversals BA and AC. So there's like two transversal cases here, right? These two lines are, you have these two transversal cases. Okay, it can be easier to kind of extend these lines so we can see the different angles. So, okay, which pairs of angles are congruent? So like this can be kind of confusing, but what you can see here is that like angle 1 plus angle 5, this entire angle is an alternate interior angle to this angle. You see? You can't mix these two transversals here. They're two distinct transversals. Okay? Now, but we can see that angle 4 is congruent to angle 2. So there you go. Part A, angle 4 is congruent to angle 2. All right. What else? We've got, so this entire angle is congruent to this entire angle. These are, as far as transversal AC, these are opposite interior angles. So angle 5 is congruent to angle 3. Okay. And is there any other direct congruence? What about angle 1? Now, angle 1 is kind of a mixture. It's going to be, when it comes to looking at the two transversals, it's going to be mixed in. So let's see. These are the only congruence pairs. What is the sum of the measure of angle 1, measure of angle 4, and measure of angle 5? Well, okay, we can see that that's going to be, you don't call that supplementary. That's just a relation between two angles, but the measure of angle 1 plus the measure of angle 4 plus the measure of angle 5, we can see that's a straight angle. Okay. What is the sum of the measures of the angles of the triangle ABC? Well, that's going to be 180. The sum of the angles, well, okay, we haven't proven that yet in geometry. So maybe they want us to prove that. We know it's going to be 180 if you have any familiarity with triangles, but I guess we don't technically know that yet, right? So, okay, well, this is, I'm not going to put measure just to make it clear, but 1 plus 5, and this is 1 plus 4. Okay, in terms of measures, but I mean, I'll put it, why not? The measure of angle 1 plus the measure of angle 5, and this is the measure of angle 1 plus the measure of angle 4. Okay, opposite interior angles. So, if we're looking for what we're looking for is in part C is the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. Okay, so we know, let's see, we know that the measure of angle 1 plus the measure of angle 5 plus the measure of angle 2 is equal to 180, which is the sum of these is also equal to 180. So let's try that. Is equal to the measure of angle 3 plus the measure of angle 1 plus the measure of angle 4. Those are also summing to 180, right? So these subtract out. So we've got the measure of angle 5 plus the measure of angle 2 is equal to the measure of angle 3 plus the measure of angle 4. Okay. But let's see, angles 4 and angles 2 are congruent, so maybe we can do measure of angle 5 plus, let's change this to measure of angle 4. So these cancel. So we get the measure of angle 5 and 3 are congruent. That doesn't give us any new information. Well, okay, no, here we go. Measure of angle 1. Okay, but 2 and 4 are congruent, so we can change measure of angle 2 to measure of angle 4. 3 and 5 are congruent, so we can change measure of angle 3 to measure of angle 5. But now look, measure of angle 1 plus measure of angle 4 plus measure of angle 5, that's equal to 180. So the answer to part C is 180. But again, we don't, if you're thinking about this from the story of geometry, we technically don't know that the sums of the angles of any triangle, the interior angles of any triangle are summed to 180 for universally for all triangles. We haven't proven that yet. So they're just giving us a preview here, a hint.